Topographic maps and geology. This can be very good tools if you know how to read them. Now, topographic maps, of course, are full of lines with numbers and symbols on it. So let's go through and see what we can do with a topographic map. First of all, maps contain symbols. That is necessary to put a lot of information on a flat piece of paper. Let's look at the map and see what can be shown. Well, it's rather bewildering. Forests can be shown sometimes as a green shading. We also have some squiggly lines on there. These are contour lines telling us the elevation. Roads and stippled lines depict trails. We have benchmarks. Now, benchmarks are interesting. These are actually survey points that have been surveyed in by means of a surveyor to give us the exact location and elevation of this point. Often there are big databases in counties and states that contain all these surveyed in markers. Benchmarks, they often have an elevation number next to it. Streams, of course, are marked in blue. Buildings may be little black squares, and any boundary between forests or national parks or counties may also be depicted. Well, let's work a little closer with that. Now, one of the problems we're going to face is how do you show elevations on a flat piece of paper, like a topographic map? Well, we use something called contour lines. And in these little exercises, you will find out how to read, how to interpret, and how to make your own contour lines. Contour lines are lines of equal elevation on the map. With other words, if you would walk along a contour line, you would never go up or down. Walking on a contour line will keep you always at the same elevation. Now, contour lines, as we've seen before, are depicted by these brown squiggly lines. And they can be read like any other text or book. Now, in order for you to understand contour lines, it is best to do some exercises from your lab. So take out your lab, and we're going to work on the isoplex and contour line exercises that are in your lab manual. Follow the instructions given, and you may pause the video every now and then to complete the exercise. Alright, here's exercise number 1. There is a function of an isoplex or contour line. By the way, isoplex means something of equal value. What happens is an isoplex or contour line has a function. Right? The function will be that it will separate two values. Now, here's a piece of a fence where it says start here, and your job will be to separate two values, in this case, wolves and sheep. After you are done, all the wolves should be on one side of your contour line or fence line, and all the sheep on the other line. Now, the line should form a closed loop, and if you observe it carefully in your exercise, there should be no sheep inside with the wolves and no wolf inside with the sheep. There are several solutions to this problem, and I'm giving you a little fence line here. Start here and see if we cannot complete the loop coming in the other end and fulfill these qualifications. Remember, for this first exercise, what you should learn is that the contour line separates values. In this case, our values are sheep and wolves. In the next exercise, you also need to separate values. You need to draw a line that separates all the 4s from the 5s. More than one line may be necessary to complete this exercise, and you also should be able to establish that your line you have drawn has its very own value. So concept 1 is still true. A contour line separates values. But there's also a second concept that will be introduced, and the second concept is that a contour line may also stop where your data ends. So if you come at the edge of your data points, since you do not have enough control over the data, you may stop the contour line and do not need to close it. Again, the line you draw on this exercise will not only separate the 4s from the 5s, it will also have its very own value, and you may try to estimate what this value might be. Now exercise number 3 is a little bit more complex. Here we're going to work with very own values of contour lines. Your assignment will be, in that box, to draw isoplus lines that have the value of 2, another isoplus line that has a value of 4, another one that has a value of 6, and another one that has the value of 8. Remember, all these little numbers in there are actually data points, and are right in the middle of that number. So here you have to have several isoplus that all need to fulfill their functions. Are they separating values, like higher from lower ones? Do they have their own value when you complete it? Give it a try. This is really the concept number 3 that we will introduce here, that the contour line definitely has its very own value. Exercise number 4 is kind of an interesting exercise. Here you will analyze a surveyor's grid. Let's just think about a surveyor came out and produced this map by surveying in grid points and writing down the elevation, let's say in feet. We see several elevation points marked. What we need to construct from these grid values is actually a map with contour lines on it. Now your job will be to start with the 500 isoplus line, and from there move up and down to draw another isoplus or contour line at the values of 450, 400, and so forth. And the set it's going up with values of 550 and 600. Now there is another concept you may need to remember as you complete that particular exercise, and that is that a contour line never splits or crosses over another contour line. Very important to remember. Now, in this exercise we need to start with the 500 line, and as you can see, we don't have too terribly many 500 elevation points on the map. Unfortunately, there were not that many that our surveyor gave to us. So what do we do now? Well, there is a process where we can increase the number of 500 height elevation points. A process is called interpolation. It's somewhat like a little bit of guessing, but much more accurate. Let's say you have 2 points. One elevation point is marked 450 and the other one 530. Now, of course, the 450 point is lower than the 530 point. Where is the 500 point on that map? Well, if you drew a little faint line between 450 and 530 and would walk along this line, sooner or later you would cross the 500 point. Now, as you move from 450 to 530, you actually would go up in elevation. But where is a 500 point? Well, if you put an equally spaced scale between the 450 and the 530 point, and then ticked off values along this equally spaced scale, you can see that your estimated 500 elevation point would be right here. Now, how accurate is it? Well, amazingly, this is more accurate than people might think. You probably will be within a few feet of the actual 500 elevation point Doing this between adjacent points one higher and one lower than 500 will give you a multitude at 500 points. So let's try this as we work through exercise 4 together. And you may then complete the map with some more points. Okay, we need some more 500 elevation points. But first let's find the ones we have. Well, there's one right there on the bottom. Another one circled red, kind of to the left in the middle. Another one up there. And that's about it. Well, now how can we find more 500 elevation points? Well, let's find two values, one above and one below 500, and draw a very faint line as we have done before. Now, as you construct the map, you do not have to draw this very faint line. If you must, to kind of give you a little visual aid, then draw it very faintly so you can erase it later. But here we have 2 points, 488 and 551. You can easily see by moving from 488 point to the 551 point that we will cross somewhere the 500 elevation point. Now, without much to do in actually putting a scale down, where do you suspect the 500 point would be? Closer to 488 or closer to 551? Well, you are right. It's closer to 488 because we are only 12 feet away from 500. Well, 551 is literally 51 feet of elevation away. So I would put my point along this line closer to the 488. Now we can continue doing this one with some more points. Here we go from 488 to 512. What would this point be? Well, it's 12 feet up to 512 and 12 feet down to 488, so I would put this point right in the middle. And pretty soon you don't have to draw these lines anymore, and you can just picture in your mind where those points might be. Let's do a few more. Here should be another 500 point. Well, what about close to 489? What about those? Again, maybe a little further out, also close to 489. You can see with the process of interpolation, we have already increased our data density for the 500 line. Let's do one more, between 489 and 555. Well, I would plot it right there, and you can see that there's a contour line slowly but surely emerging. Let's find some other 500 points. I won't draw the lines anymore. Just plot the points where I see one value below 500 and the other value above 500, and just imagine the line between those. There would be one probably here between the 468 and 539. What about 468 to 525? Well, 439 to 517. Well, you can see my points are starting to come about. And I'm getting a pretty nice outline of my first contour line, the 500 line. Well, I think the data density is kind of nice. Remember, where the map ends, I can stop, and we can now connect our 500 points. When you do this, please use a splining process instead of straight lines. There are rarely such things as straight lines in nature, so it should be a nice curve going around, showing the first elevation line of 500 feet. Well, this was easy. Now the other ones are much easier to draw because they follow the shape more or less of the first contour line just established. So let's do the 450 feet contour line. Again, let's interpolate more 450 points. In this case, we need to find values below 450 and values above 450. What about between 488 and 382? Okay. What about 382 and 457? Well, you can see we're doing the same thing. We can continue doing so and get more 450 points. Here's one between 439 and 517, 439 and 483, and we will continue doing that. Well, now that we have this one completed, we can draw another contour line, the 450 contour line. You can see that the second line follows more or less the shape of the first one. Now your job will be to complete the rest of the exercise and see if you cannot come up with the correct position of the other contour lines by increasing your data density through interpolation. Now, in order to use contour lines, the vertical distance or contour interval must be defined. Well, in this following model, my contour interval is 10 feet. Let me illustrate. Let's say I have an aquarium with an artificial island in it. I pour some water in it, and this would be my sea level, or water at zero level. Now, if I look down from the top into the aquarium, I would see a nice outline or coastline of that water. Since water is perfectly horizontal, if I took now a waterproof pen and marked the spot where the water is touching the solid land, I would get my first contour line, or the zero elevation line. Now, what if I filled exactly 10 feet of water into my oversized aquarium? Well, more land will be submerged. If I look down again on top, I can take my waterproof marker and outline the coastline. I have created the 10-foot contour line. What if I added another 10 feet? Well, the same thing happens again. If I look down, I can take my waterproof marker and outline the contour lines around that. What about another 10 feet? And the same thing happens. Now, if I drain the aquarium and see what I have marked, I would come up with a pattern of contour lines that depict the elevation of 10, 20, and 30 feet, like in that map. Water can be a very interesting way of showing contour lines. Here's a lake that drains slowly, and you can see with each water level as it falls that contour lines are merging exactly at the coastline of these water levels. If you would walk around and draw a line at this coastline, we would make exact contour lines in the process. How do you generate a topographic map from contour lines that you would draw on a three-dimensional object? Well, this animation shows it nicely. We're drawing a bunch of contour lines while taking the three-dimensional object away, and then we lay it down flat and look down at the top just in a map. Drawing contour lines. Once you, of course, have established your map and want to draw contour lines, there are a few conventions that you should know about. Index contours are bolder contour lines. They contain a number that depicts the elevation. The reason why we don't write a number on each contour line, because when they get tight, like in mountainous terrains, we would clutter the map too quickly. However, we can fill in the spaces between index contour with our much finer intermediate contours. Once we know the contour interval, we can always tell the vertical distance between those contour lines. Well, here is a bolded index contour with intermediate contours to the left and to the right of the 550 line. However, since we're talking about a flat piece of paper, it is often hard to see a hole in opposition to a mountain when we come across one. like the crater of a volcano. How would we depict that? Well, if my elevation all of a sudden changes and doesn't follow natural convention, then we put little tick marks on our contour lines that depict a downhill slope, or a depression, or a hole. Meteor craters, for example, or volcanic craters, are a perfect example of how this would be drawn. Here is a three-dimensional representation of a volcano and what the contour lines on a map would look like. As we climb up toward the volcano, we eventually hit the 300 feet line. Then comes a ridge, and then we would all of a sudden go downhill into the crater that is depicted by these contour lines with the tick marks on it. Now, what about the so-called contour interval? That is the vertical distance between my contour lines. How can we tell? Well, let's look at the following maps. Here is one, and that is fairly easy to tell because the contour interval is written on the bottom. Contour interval of 20 feet, right there below the scale. Now what if there is no contour interval written? Like on this map. We have some index contours, and we should be able to figure out what the contour interval of this map snippet might be. I'll see an 800 and a 900 index contour line right there. There are 4 intermediate contours between those index contours. It should be easy to figure out what each one of the elevation changes should be. Well, at this 100, of course, 100 feet between the two, divided by these lines. If we added 20, another 20 to make this one 840, another 20 to make this one 860, another 20 to make this one 880, and another 20 would get us up to 900. Then we can easily see that my contour interval here is 20 feet. Now that you know a little bit more about contour lines and what they mean and how they depict elevation, can you figure the elevation of the following points from a topographic map? Here's a topographic map with a few places marked. Let's start with point D, right there. What do you think would be the elevation for point D? Now look closely at the contour interval. Figure it out first, then at the index contours, and you should come up with the exact elevation of this purple square in point D. You may pause the video before I continue and give you the answer. Since it sits right on a contour line, the elevation of this point is 4,360 feet, because it sits on the 4,360 foot intermediate contour. If you haven't figured it out, the contour interval of this map is 40 feet. What about point G? Try to do the same. Again, you may want to pause the video, and I will give you the answer in a second. Point G again sits directly on a contour at 4,080 feet. Again, you should be able to deduce this from the index contour and the intermediate contours. What about the top of the hill here at point F? Now this point does not sit on an exact contour. Can you figure it out? Well, again, pause the video. You may have to guess a little bit and see what the elevation might be. Well, this elevation you can't tell exact because you don't have the benchmark or elevation on the top of this mountain. However, we know that it must be higher than the last contour, but not as high as the next 40 foot of contour that would show up. Hence, it would be a good idea to just split the difference, and therefore the idea that it is about 20 feet higher than the 4,760 foot line to about 4,780 foot is a good one. How close will you be? Well, you will be within 40 feet of the actual elevation because of the 40-foot contour interval. Sometimes it is necessary to describe the terrain on the map in words. Now, that can be rather lengthy, and there's a simple way of doing it to tell the reader if you have a rough terrain or a fairly smooth terrain. It's called relief. The relief is basically identified as a difference between the highest and the lowest point on the map that is visible to you. Let's look at our map again. Let's find the highest point first, which should be fairly easy to do because it's usually the top of the hill, and most of the highest points in the world have been carefully measured in or surveyed in, so we should find a benchmark. So, what is the relief of the map? Here's my high point, benchmark 4861, 4,861. That was easy to find. We're going to mark this one down as my high point. But what about the lowest point? Well, the lowest point is easy to find if you follow water. Water flows downhill, and there's not too many rivers on that map. There's one in the upper left-hand corner and one in the lower right-hand corner. The one in the lower right-hand corner appears to be lower than the one in the upper left-hand corner, so we use this as a low point. Again, there's an index contour line showing, and that is our low point at 3,000 foot index contour. Well, what is the relief of the map? 4,861 feet minus 3,000 feet equals 1,861 feet between the highest and the lowest point. That tells me it's a little bit mountainous, and you have to climb a little bit to have an elevation gain of almost 2,000 feet if you want to walk around that area that the map depicts. What about contour lines and running water? Now this is an interesting little feature. If we look closely at running water and magnify this area where it crosses contour lines as my rivers flow downhill here, you can see that my contour lines do not cross a river in a straight line. Actually, they make a very, very distinct V, a V shape. One rule that you can remember and write down: the V's that contour lines describe as they cross rivers always point uphill or toward the head of the river, where it comes from. By the way, this also helps to figure out dry riverbeds. As you look at the map, look at V notches that point uphill, and this is usually water channels as they move down. Here's one of these dry river channels, and you see fine notches. Not a good place to put your tent if you like to go camping there. However, there's a much bigger river on the other side. Again, you see some very pronounced V's as the contour lines cross those rivers. This is true for all rivers and all contour lines. Now I hope you have had the chance to get familiar with topographic maps a little bit and the basics of it, so you can use them as an interpretive tool for deciphering the geology.